Morning. Let's get started. How's it going? Yeah. So today we'll finish up on caching, and then we can move on to prefix sums, which is the next topic. People okay with PA1? I think is due Friday, but you can have until Sunday to do it. People okay with that? Any issues? Okay. Cool. Yeah. So last time we were doing this cache-oblivious stencil, and if you remember, we had two algorithms for computing a stencil. One is a looping version, where you just directly go left to right through the layers, and then one layer at a time. And then the cache-oblivious version is this trapezoidal decomposition. So in the rest of this part, I'm going to talk a bit about the actual practical performance of these kinds of things on shared memory machines. So this is a simulation of the 3-point stencil starting with 1D. So this is the looping version, and this is the trapezoidal decomposition. And the purple is cache misses, and green is cache hits. And this is simulation n, which is the number of horizontal points, is 95. T, which is the number of vertical rows, is 87. And they simulated a fully associative LRU cache with a B, which is the number of elements that you can fit on a cache line, as 4, and M as 32. M doesn't show up in the bound for the looping code, so it doesn't matter too much for that one, but it does show up in the bound for the trapezoidal version. And this is just like a simulation that you can write. The cache hit latency is 1 cycle, the cache miss latency is 10 cycles. Of course, this is an approximation, but it does tell us something. Green, like the colored part, is the progress that the thing is making. So given the same amount of time, the simulation tells us that the trapezoidal version is proceeding much faster than the looping version. So it seems like this should be great, but of course this is simulation, and in reality things are maybe a bit more complicated. So this is what happens when you actually run the code. So given a 2D grid, so in this case the spatial part is 2D, and then the temporal part is the third dimension. So like you can imagine a 2D grid, and then the time is growing up in like a rectangular type of prism. And here, in this just example running, they found that the looping version was about 1560 iterations per second, and the trapezoidal version is about 1830 iterations per second. So this is much closer than the theory would tell us, at least on one core, because if you remember, there's for d dimensions, you see a m to the 1 over d in the denominator for the trapezoidal decomposition. So we should see a root m in theory in the denominator for the trapezoidal version, which is much more than a factor of less than 2, because m is usually something like on the order of kilobytes. So why? What reasons might they be so close to, for what reason might they be so close together? And this is running on one thread, or one core. Oh, sorry, this is a question. Yes. Like function call overhead? Yeah, this one. What about the system? Yes. Yeah, it's a good point. At what point do you start? So, like, in some sense, the cache analysis is focusing on bandwidth in some sense, because like the lower bound is going to be nt over b, because that's the minimum. That's like the amount of that's the amount of misses that you have to take to read the entire. Or sorry, no, nt over bm, I guess. But are you saying that like you're not hitting the memory bandwidth, and you're kind of in like a latency bound scheme? We want to be in a bandwidth bound scheme because bandwidth is faster than latency. Good. So in reality, also in memory systems, we have, I don't know how much people know about the memory subsystem, but in the theoretical model that we just had, we counted cache misses. In reality, different cache misses have different costs. So if you read memory close to where you currently are, that is faster than reading memory far away from where you currently are. in a spatial sense, because in real hardware, you have things like prefetching. And prefetching means if you read one cache line, then you read, the system will bring in like the next few cache lines for you, because a common pattern is that you might loop left to right, like a super common pattern in algorithms. You want to do a sum, you read the whole array left to right. Or you want to, I don't know, do element-wise addition or anything like that. And so hardware designers give you prefetching, which makes it really fast to read memory sequentially. So that's why, so it's not so much that the trapezoidal version is slower than we think it would be, but it's more that the looping version is faster than we think it should be, according to the theoretical model of counting only cache misses as unit costs. And there are fancier models that take into account less, basically like if you read sequential memory, it will, in the analysis, it will have less cost by introducing some other constants. But the caching model that we just did, where you just count every access as one, is like still the traditional, like when you add more complication, then you lose something in ease of analysis. So there's some trade-off in, there's always trade-off in analysis models like that. Questions? So next, this is not a theoretical thing. We're just going to do caching and parallelism from a practical perspective. So when you introduce, so in reality, we want to make the code both cache friendly and parallel, because then we can use the most of our machine. And in practice, minimizing the cache misses in the serial execution or the serial projection, which is if you write the parallel code and you have some spawn and sync, the serial projection is just if you remove the spawn and the sync keywords. So that should be a correct algorithm, just top to bottom. And the cache misses in parallel is at least the cache misses in serial, because it's not really clear how it would be less. Yeah, go ahead. Oh, like, oh, I'm recording on my phone. Yeah, sorry. Anyway, should be fine, I think. Yes, thank you though. So we want to minimize the cache misses in serial, because that will also minimize the cache misses in parallel. We will always incur at least as many cache misses when we add multiple cores compared to when we have one core, because when you have multiple cores, you have issues like different memory. Like, for example, we were talking about true and false sharing, which is something that can always happen in parallel, and that adds additional cache misses. In addition, if you have, for example, like non-uniform memory, which happens in a lot of today's machines, then you may get additional cache misses, like if memory needs to transfer between different threads. So ideally, we would like to parallelize this code. And so we have two kinds of cuts. One is time cut. And time cut seems hard to parallelize because there's this dependency between the bottom part and the upper part. We have to compute the whole bottom trapezoid before we compute the top trapezoid. Maybe there's some hope that we can parallelize space cuts. So initially, with this single cut formulation, we can't parallelize this because the right side depends on the points in the left side, at least in this boundary. But we can cut it slightly differently. And this is how you would parallelize it. So we have this trapezoid, and rather than cutting one, originally we cut one line. Now we can cut two lines here. And then these two trapezoids marked with 1 can proceed in parallel because they only depend on the points within these things. And then once we have computed both sides, then we compute this triangle too. And then we can do the reverse. If the trapezoid is upside down, then you just cut it with the opposite slope. It's an example of how the performance looks. So running this grid of 3000 by 3000 for t equals to 1000 on 4 processors. We have this looping code, serial and parallel. The looping code is easy to parallelize. Like the layers, the time steps cannot be parallelized, but the spatial steps can happen in any order. So that part is really easy. You just put a parallel 4 on the inner 4. And in this example, we see about 2x speed up from about 130 seconds to about 67 seconds. And in the trapezoidal version, the parallelism is more complicated because we have to do these different, the space cuts in a different way. But the original time is about 67 seconds, and then it goes down to about 17 seconds. So that's almost a 4x speed up on 4 processors. And that's almost the best we can hope to do. We have 4 processors, so the max speed up we can hope for is about 4. And even though the parallel looping code should have a lot, so the parallel looping code, it's really easy to parallelize. You just put a parallel 4 there. It achieves less than half the potential speed up, even though it has much more parallelism. And the reason for that is because often when you have parallel scaling issues, they're not an issue of how much parallelism you have, but an issue of how much locality you have, because you may be bottlenecked by memory bandwidth. Yeah, so sometimes it is not an issue of, anyway, to recap, sometimes it is not an issue of how many processors you have, but another possible bottleneck is just the time that it takes to transfer the memory. And if you can minimize that, then you can alleviate one of the potential bottlenecks. Some reasons that you might be not getting the speed up that you want to get. One is that you have insufficient parallelism. That's definitely possible. And that is something we can analyze using work and span, like we did earlier. Another one is scheduling overhead, like either function call overhead or it costs something to spawn a task. Like you have to move the context, a different thread needs to start up, that costs something. And usually this is okay if your work pieces are not super small, like you just need to do enough work on the thread to amortize away the cost of spawning the thread. Another one is lack of memory bandwidth. This one, there's multiple ways you can debug this. Like a high budget way is you can physically reduce the amount of hardware you have, and then you can decrease the memory bandwidth. And if your program gets slower, that's one way to know that you are bottlenecked by memory bandwidth. Another software level way is you can run P copies, where P is the number of processors you have of your program. And if your thing gets slower, then you know that you are bottlenecked by memory bandwidth. The last one is contention. So I didn't really talk about locking, but locking is a form of mutual exclusion. And mutual exclusion is like if you have a shared resource, which processors can access it at one time. And if only one processor can access it at a time, then the other ones have to wait, and they will be delayed. So that's locking, which is one form related to parallelism. And then there's true and false sharing, which we talked about a couple times ago, which is a type of cache miss that you get only when you have multiple processors. There are some tools that can tell you if you have lock intention, but it's a bit complicated because it tells you you have to execute it. Like it doesn't tell you how much potential you would have for lock intention. Then another one is potential for true and false sharing is even harder because you need to know something about the memory access pattern. This is the last bit of this topic. You don't need to know this exactly, but this is just like there are many other cache-oblivious algorithms. I think they came up in the 90s, and people have been writing papers on them since then. One basic one is for matrix transpose or addition. Straussen's algorithm, which is a subcubic matrix multiplication, fast Fourier transform, which we will talk about later in this class, and LU decomposition. And just notice that they have these bounds have factors of B and M, so they're in this caching model. You don't need to ever memorize this or anything. This is just it's just to show that this is something that people work on. And this is also this class of cache-oblivious data structures. So it's not just for algorithms. More recently, people have been working on cache-oblivious data structures, which are you want to achieve lower bounds in data structures without knowledge of the cache parameters. So there are versions like, for example, B trees, which are a classical cache-friendly data structure. They're cache-oblivious B trees that don't need to know the cache parameter. Questions? Yes? Yeah, sharing misses are hard to detect because in some sense they depend on the how the scheduler orders the threads. Because like they would happen if two threads or two processors are trying to access the same memory at one time, and that depends on like so like spawn and stuff like that tells the processor that logically you can do this work in parallel, but it doesn't. It's the job of the scheduler to actually run the threads in parallel and order the work. And so depending on how the threads actually get ordered, then you may or may not incur sharing misses. Because like it could you can tell, for example, like you can tell in the code, like, oh, this part can be spawned, this part can be synced, but like the scheduler may decide not to do any of that. And it's a valid execution to just run the whole thing in serial. And so then you have no sharing misses. That's one extreme case. But in general, yeah, in general, whether you incur sharing misses depends on the order, like the lower level scheduler, um, which can change also. Like that's a systems level thing that you can modify. Understand? Thank you. Great. So that is the end of caching, and I think that should be all that you need to do the homework. And now we're going to move on to prefix sums. Do people already know about prefix sums? Okay, great. So this is exciting. Prefix sums they're a really nice algorithm, and if you learn one algorithm in this class, let it be prefix sums, because once you see them, they will be everywhere. And they're kind of like this one, I would say like maybe they're this one canonical example of a parallel algorithm. Oh yeah. Just a reminder, in 2 weeks we have an exam in class. It will be on everything starting from the beginning up until and including prefix sums. We did efficiency, speed up scalability, work in span analysis, cache complexity, and prefix sums. Mhm. I will upload some practice questions. Yeah. But I think there was some confusion last time. So I will upload practice questions, but like the content will be the same, but maybe not the exact format or like style of question, but the ideas will be the same. Mhm. Yeah. Oh, and you can have you can bring one sheet, like just a letter size sheet. You can write whatever you want on it. Mhm. Yes. Oh yeah, I extended it to Wednesday because yeah, just because I was a little bit slower through the caching. So I will update the syllabus. Thank you. Mhm. Questions, concerns? All right. So prefix sums are kind of like a basic looking algorithm. You have an input array, x0, x1, up to xn minus 1. So there are n elements. And you want to output an array y, y0, y1, up to yn minus 1. And this is, so the arrays are the same length. And you can define prefix sum recursively, where y sub k is if we're in the first position, then y sub 0 is just equal to x sub 0. Otherwise, y sub k is equal to x sub k with some operator, y sub k minus 1. So you can kind of think of it as like computing. So the first one is just the first element from x. The second one is the sum of the first two. The third one is the sum of the first three, and so on like that, up until the end. And this is an arbitrary operator, often sum, but it can be multiply, max, min. It just needs to be binary and associative. So here are some examples. We have two arrays. We want to compute the prefix sum. So A is the input array, and B is the output. So the first element is 3. Those are matching. The second element in the output is the first two added up. So 3 plus 1 is 4. Then the third one, you add up the first three. So 3 plus 1 plus 1 is 5. And all the way until the end. And you can, like I said, it doesn't have to be sum. Sum is usually the easiest to see it as, but it can be, like, for example, max. And so max would just be like, you do this left to right. 3 is bigger than 1, so 3 goes there. 3 is also bigger than 1, so 3 goes there. 3 is bigger than 2, so 3 is there, and so on. So a natural serial algorithm to do this is just you iterate the array left to right, and you keep track of like the partial sum so far. Like you're trying to fill in b, and you have a I minus 1, and so you just do like, or sorry, you have b I minus 1 if you do it serially left to right. So you just do like b I minus 1 plus a of I, and that would give you b of I. There's two variants of scans. One is inclusive and one is exclusive. These are just like, the algorithm to compute them is pretty much the same, but it's just like in some problems you want the inclusive version, and some problems you want the exclusive version, which is that if it's inclusive, then you include x sub k when you compute y sub k. So here, like x sub 1 is 1, x sub 0 is 3, and then you add them up to 4. The exclusive version, you don't include x sub k. So like this just starts with the identity. This one is 3, which just includes every. So this one, like the exclusive version, includes everything up to, but not including the current position. And inclusive is everything up to and including the current position. If you have solved the inclusive version, oh yeah, so you can easily get the inclusive version from the exclusive by just adding in x sub k. Like suppose that you have computed, if you have computed this thing, you can get this by just adding a in element-wise. Going back is slightly more complicated. You can go back if you have an inverse for your operator. So addition has an inverse, but not every operator has inverse. Like max, for example, doesn't have one. Okay. And then another variant on prefix sum is suffix, which is just the other way. So if prefix is like left to right, you're keeping these running sums. Suffix is right to left. So you start from the rightmost position and you do these partial accumulations. Make sense so far? Questions? So our goal is to parallelize this thing. And it looks, at first it looks like it's a bit hard to parallelize because like the serial algorithm, every iteration depends on the previous iteration. But we do want to formulate work-efficient parallel algorithms for the problem. So yeah, so can we parallelize this? In serial, it's straightforward. It's something like n operations. The ith iteration depends completely on the previous one, and this is just like 5 lines of code. You iterate through n, you compute y of I is y of I minus 1 plus x of I. So the first try we can do is we can reduce, if we have arbitrarily many processors, because this is work span analysis, and we can put one processor on each element and sum up everything before that, using some tree-like reduction that we were doing in the previous lectures. So that will take log n in the last position. It will take something less than log n in the other positions, but you can do them all in parallel. So you have a parallel for over the positions, and then each one does a tree reduction. It's log n plus log n. The total span is log n. And so the parallelism is good, seems like, but the work is poor because that's something like order n squared work, because we're recomputing the sums. Like position 1 or position n has to do all the sums left to right. Position n minus 1 has to do all the sums from 0 up to n minus 1, like that. So this was good in terms of the span. Log n is not bad in terms of the depth, but ideally we would like to bring this work term down because we want to design work-efficient algorithms, which are algorithms that do no more than a constant factor of the work compared to the best serial algorithm. Remember that the best serial algorithm does n work, so we need to bring this down a bunch. One classic algorithm to compute the prefix sum is from Hillis and Steele, 80s? Oh yeah, from the 80s. And this is one classical example of what are called data parallel algorithms, which are popular now due to GPUs. And this is how it works. So this is like in some sense, like it's a summing network. So each line is one of the elements that we started with. So each line is one of the initial elements in the array. And plus is the sum that we're computing. So like this plus means that element 0 and element 1 are getting added together. And then, so the distances between what is getting summed grows exponentially. So like at first they're 1 apart, now they're 2 apart, in the next level they're 4 apart, and then they're 8 apart. These are the pseudocode. So for I up to log n, inside the parallel 4, for j up to n minus 1, you add up this summation. Yeah, so what is the work in the spin for this thing? So we can start with the work. The work you just get by ignoring the parallel 4 part. You just put a 4 there. Yes, good. So yes, so that is n log n, because the outer loop is log n, the inner loop is n, and you just multiply them. What about the spin? Why is it log n? So the outer one is log n. So the first, what is the span of the first iteration? And the span of the second iteration? Oh, sorry, the iteration of the outer part. And so what is the total span? Good. Is everybody clear on that part? So there are n outer loop iterations. Each one has span log n, because the span of this parallel 4 is log n. So that's log squared, because you just add up log times. Yep. So the work is n log n, the span is log squared. And we're getting there, but it's still not work efficient. Again, we want to bring this work down to n. And so in the 90s, Guy Blella came up with this really beautiful algorithm for prefix sums that is work efficient and achieves span log n. And basically, the high level idea of how this works is that there's 2 phases. One is called upsweep and one is called downsweep. And the upsweep does just like, this is like a tree-like reduction, just like any tree-like reduction that we would compute for the sum. And the idea is that, so when you compute, if you only cared about the sum, like the total sum of every element, then you would just keep around this last element and you wouldn't care about any partials that you computed. But because prefix sums, you care about all the partials. In the upsweep, you keep track of every partial sum that has been computed so far. And basically what is going to happen is in the second phase, in the downsweep, you push those partials to the right. Because you need, like, for example, this element is going to be the sum of this thing plus this thing. This thing is the sum of these, and this thing is the sum of those. So the upsweep basically computes the partials of every power of 2, and the downsweep pushes, kind of like expresses every element as the sum of power of 2 index elements. Yeah, so each phase is n work, because the work is decreasing exponentially as you go up the layers, and there are log n layers. And here, the work is increasing exponentially as you go down the layers, but there's also log n layers. And the bottom layer is n. So this is an example. Oh yeah, go ahead. This one? So what is the span of the first iteration? Just ignore this part first. What is the span of the first iteration of the outer for loop? And then what about the second one? And so how many are there? Yeah, so you add up, like, the first one is log n, the second one is log n, and you have log n of them. Does that make sense? So we can do an example. We have this input array, 13, 9, -4, 19, -6, 2, 6, 3. And the first layer of the upsweep, we add up neighbors, just neighboring pairs. So 13 plus 9 is 22, negative 4 plus 19 is 15, negative 6 plus 2 is negative 4, 6 plus 3 is 9. And, well, this one is already done, but the rest of them are not finished because 15 needs to, like 15 is just the sum of these two. But this 22 is done, it's there already. And now we do distance 2. So 22 plus 15 goes to 37, negative 4 plus 9 goes to 5. And notice that now this one is also done because these were the sum of this pair, and this element is just the sum of these two groups. And so this is recursive. Like if this was your entire, let's say that your array was just like size 4, then this would be the full sum of the array. This would be the full sum of the array. And these two, again, go here, negative 4 and 9. And this, similarly to this left half, this is also, this 5 is the sum of this entire right half in the beginning. And the last step, now they're distance 4 from each other, 37 plus 5 goes to 42. And that is the sum of the entire array from the beginning, because this 37 is the sum of this left half, this 5 is the sum of this right half, and you add them together, and that's the sum of the whole thing. So after the upsweep, the last element is finished in terms of the sum, and some of the other intermediate elements have been finished, like this one, this one. Actually, every power of 2 position has been finished during the upsweep. And basically what is going to happen in the downsweep is that this 37, which is the sum of this left half, it needs to get propagated into these 4 elements. Or not the last one, I guess, because that's already done. But these 3 elements, this 37 needs to go into them to compute the prefix sum. And so that is the point of the downsweep, is that we're going to push it in a similar tree way. So in the downsweep, 37 gets, so these are distance 2 from each other, 37 and negative 4. That's 33. So negative 4 was the sum of these two things because of this pairwise addition. And 37 is the sum of these 4. So the total sum for this thing, or the total prefix for this thing, is negative 4 plus 37. 33 here. And then now this thing also needs to get pushed into the right. So it needs to get pushed into all 3 of these elements. But because in the first step of the downsweep, it has already been the middle one, now that can push it further into the right, and this can push it this one distance away. And the same thing happens for like recursively in the left half. The midpoint of that needs to get pushed to the right. And that is it. This is the end of the prefix sum. 13, 9, negative 4, 13 plus 9 is 22, plus minus 4 is 18, and so on. Questions? So how do you actually write this in code? You can write it recursively, like with actual divide and conquer. You can also write it iteratively. So this is how you would write it iteratively. The first upsweep goes up to log n, and there's a parallel 4 inside. The distance between the pairs changes. It goes up with d, with the log n. So the first one is they're just neighboring pairs. The second one is they're distance 2 away from each other. So on. And then you just add on. So like this is the thing on the right, and the thing on the right gets the sum of the thing on the left plus itself. And in the downsweep, it's just the reverse. So now instead of the distances growing between the elements, the distances are shrinking. And this is, now the thing on the right gets the thing itself plus the thing on the left. Okay, so you start with the easier one. What is the work? Let's go back. Mhm. Is it O of n log n for the work? Okay, so let's count up the work on the upsweep. So there are log n iterations on the outside. And the first one, how many, so like when d is equal to 0, which is this layer, how many additions are happening? Yeah, so just in the first iteration, when d is 0, just consider there's just this layer of additions. How many additions are there in terms of n? Order n? Theta n? Mhm. Because there are n over 2 iterations, or sorry, there are n over 2 additions. Like you have n elements, and pairs are getting added, like just your left neighbor right directly to the left of you and yourself. So in the first layer, there are n over 2 additions. And what about in the second layer? Good. And then the next one? And if you add them all up, how many additions is it? Like n over 2 plus n over 4 plus n over 8, that one? Um, is how many in, like up to, um, theta n squared? There are log n of them. So like, it's like n over 2 plus n over 4 plus n over 8 up until 1. So like, what is, how do you say this? Like, the first one is n over 2. The second one is n over 4. That is 3n over 4. And then they keep exponentially falling off after that. And so the sum is actually n, because like you sum up log n of them. Is it easier to think about it the other way, like 1, 2, 4 up to n over 2? Like this is just the reverse. Is it clear to people why that's n? Mhm. Mhm. Uh, yes, you can think about it. Right now we're just in the work, so we don't have to worry about the forking part yet. So the work of the upsweep is n, because there are, like if you sum these up, n over 2, n over 4, n over 8, so on, they'll sum up to theta n additions. And in the downsweep, we have a similar story. The lowest level, it's just like in the reverse, like the first one is 1, the second one is something like 2, and so on. But you could think of it as like bottom up if that's easier. Like this is n over 2, this is something like n over 4, all the way back up to 1, which is again n. So that is the work. And now we can go to the span. So there are log n outer iterations. And what is the span of the first iteration? Mm-hmm. Yes, good, because there are n over 2 sums, so you can do them all in parallel. That's log quantity n over 2. And the second one, like, so the second iteration, when you come back around, there are n over 4 additions. So that would be log n over 4 and so on. And then, so yeah, maybe this is what you were saying, that you can express it in this recursion. So the work, um, Does this work? What? Should be 1 maybe. No, because if it was 1, it would be log. Oh yeah, because n is dropping off. Okay, I got it. So in the first layer, this is plus n. In the second layer, this is plus n over 2. So the total work is n. And then the span is this recursion. This is half plus 1. And each of those goes into half like this. So the span is log n. So this is nice because the work is order n. And remember that we wanted to match the work of the serial algorithm, which is also almost exactly n additions. So yeah, so like I was saying earlier, this is kind of like prefix sum looks really simple. Like when you do it serially, it's just left to right addition. But to make it parallel, you have to kind of come up with these fancier algorithms because it looks like there's dependency all the way down the line. Questions? Okay, so we did the shared memory part for prefix sums. And there are nice algorithms for prefix sums in shared memory, and there are also nice ones for prefix sums in distributed memory, which we will do next. But before we go to that, I think I didn't get to this last time, so we will do it. I want to talk about communication patterns in distributed memory, because this is something that we have to talk about when we do any algorithm for distributed memory, which is like you have a bunch of processors, and how are they allowed to communicate with each other? Like which ones are connected, and can they all send to each other or not? It's not something you have to worry about in MPI really, because like it's hidden from the programmer. Because in MPI you just say like, I want this processor to send to this other processor, and logically they will send them to each other. But under the hood, like in the physical connections, they may not be directly connected to each other, and so there needs to be some kind of routing potentially. So we modeled communication. Previously, we talked about factors like mu and tau, which are respectively bandwidth and latency for analyzing the cost of communication. And when we model communication, communication can happen in parallel, which is that each processor can send to, like for example, let's say we have 4 processors. Processor 1 sends to processor 2, and processor 3 sends to processor 4. Those can all happen in parallel and independently. So the cost is not like 2 tau, the cost would be tau. More formally, each processor can send at most, in every time step, each processor can send at most 1 message, and each processor can receive at most 1 message. So if 2 processors are sending to the same destination, then it has to process those those 2 messages in 2 time steps. And so to avoid conflicts, which is like 2 processors are sending to the same process, then we have permutations, which are like you have n processors and you randomly shuffle the destination processors so that everybody is sending to everybody. Everybody is sending to a different processor. Yeah, and sometimes when we write the permutations, we can omit the sources because the sources are always in order like 0, 1, 2, up to p minus 1. But the destinations here are like wherever the source is sending to. So this is an example of a permutation. Processor 0 sends to processor 5, processor 1 sends to processor 0, and so on like that. And in this round of communication, it can happen in, assuming that everybody is sending only 1 message, this entire permutation can happen in 1 time step, assuming that they're all connected to each other. And yeah, so permutations are a nice way to avoid communication bottlenecks. But one problem is that like when you actually have hardware, it is unlikely that all the processors are connected to all the other processors, because that would take at least p² links. Like you have p processors, and each one, to fully realize arbitrary permutations, each one would need to be connected to each other one, which is not something that can happen when p grows very large. And so it would be really nice if we could have things that enable arbitrary permutations, but we cannot, in practice, like the issue is that there's a lot of communication patterns that the arbitrary permutations can. So if you allow arbitrary permutations, there are p factorial possible patterns, like there are p factorial permutations, and that's assuming that each one is like fixed size, so that ignores variation. Like different processes might want to send different size messages and stuff like that. So that's additional variation in the actual communication pattern. And that's also assuming that everybody wants to communicate in lockstep, which is maybe not true as well. Yeah, so if you have p-squared links, you could realize this. You could realize arbitrary permutations because everybody would be connected to everyone else, and you could just directly send on some link. However, p-squared is too many in reality, and ideally, we would like the number of links to be something like closer to p. And there is a network, a theoretical network called the Spinnis network, that you can realize arbitrary permutations without conflicting with about theta p log p links. However, this is mostly a theoretical thing because it requires a centralized planner to do the routing. And so like it is often expensive to run this planning algorithm. And so like this is, yeah, so these are like real concerns when you make these distributed memory networks because you cannot actually connect every processor to everyone else. But from a programming perspective and from a performance perspective, you want arbitrary communication to be as fast as possible. And so rather than arbitrary permutations, for a long time people studied these things called hypercubic permutations. And hypercubic permutations are this classical, they're a subset of permutations. And this is one way that you can visualize it, which is that if you have basically it's a hypercube. So like if you have d bits to represent you have d bits to represent any rank. You have 2 to the d possible processors, and the processors that are connected differ by only 1 bit. So when d equals to 3, for example, like this 0, 0, 0 is connected to 0, 0, 1, which differs in the last bit, 0, 1, 0, which is differing in the middle bit, and 1, 0, 0, which is differing in the first bit. And there's the same property for all the other ones, like 0, 0, 0 connected to, or sorry, 0, 0, 1 connected to 0, 0, 0. This is changing in the middle bit. This is changing in the first bit. And so this is really popular in like early distributed memory computing. And the reason why is because a lot of, so this cannot efficiently route arbitrary permutations, but it can efficiently route permutations where every corresponding pair differs by 1 bit. And it turns out that there are a lot of nice algorithms that can come out of just that property that we will see. And so, yeah, there are a lot of nice algorithms on the hypercube, and for that reason, they built hypercubes in early distributed memory machines. Yeah, so this is just an example. If d equals to 3, d is the number of bits that we have, and p, which is the number of processors, is equal to 2 raised to d. So here p is equal to 8, p is equal to 3. And this is one example of a hypercubic permutation where everything differs on the last bit. And then here, everything would differ in the middle bit, and there, everything differs in the first bit. So 0, 0, 0 is 1, 0, 0, which is 4. And here, 0, 0, 0 goes to 0, 1, 0, which is 2. So we can do an example problem using hypercubic permutation. We can go back to sum. So given n numbers, we want to compute the sum using p processors. And the serial runtime is, of course, n. You can just do it left to right. The parallel runtime, we said before, was n over p plus log p. And this log p is the communication. Like this n over p part is just the local sum in the beginning. And the way we can do that communication part using hypercubic processors is that like the hypercube lends itself really well to these tree-like reductions, because in the first layer, all the neighbors like distance 1 away from you communicate, and that's just differing in your lowest like least significant bit. And the things that are distance 2 away from each other differ in 1 to the left of that, and 4 differ 2 away from that, and so on. So the communication can happen in rounds, and in each round, your neighbor is just if you flip the bit starting from right to left, and there are log n rounds, or log p rounds, because d is log p. And this is just a picture of how the communication works. So the first layer is everybody is sending to your neighbor 1 away from each other. The second layer is everybody is sending to the neighbor 2 away from each other. The last one is sending 4 away. And you can get these indices by just flipping the bits right to left. Or you get your neighbor by flipping the bits right to left, where each layer is, you chose a different bit position. Oh yeah, this is just saying like in the later rounds, not everybody has to participate. So for example, like this one is done after the first round. This one is also done after the first round. Questions? So it is important to know about hypercubic permutations because we will be talking about them a lot in the remainder of the class. And yeah, and the reason is that they lend themselves well to a lot of these tree-like reduction algorithms. And it turns out that in a lot of algorithms, you don't need arbitrary permutations. You can get nice bounds using just the hypercube. Like for example, we will use it to do parallel prefix. And the reason that makes sense is because parallel prefix and sum are very related. And we just saw the algorithm for sum using the hypercube. So yeah, so we're going to use divide and conquer on the different processes in this distributed memory model. And for parallel prefix, the base case is just 2 elements. So we compute s sub 0 and s sub 1, and s sub 1 is just x0 plus x1. S0 is just x0. So this is kind of like the direction that we're going to go, that that we start with these neighbor summations. And then kind of like in the shared memory version, they're going to get farther and farther. So this is how it's going to go. We have n processors to begin with. Let's just start with p equals to n. So we have n processors, we have n numbers, and we want to compute the parallel prefix of this array x sub 0 up to x sub n minus 1. And so in divide and conquer, we split this array of size n into 2 halves. This one is 0 up to n over 2 minus 1. This is n over 2 up to n minus 1. And assuming that we have a recursive algorithm to compute the parallel prefix, in the end, we will get the parallel prefix in the left side and the parallel prefix on the right side. This is like a similar thing that we were doing in shared memory as well. And yeah, so this left half is done. Like this is just the prefix on the left half. But this right half is not done because we need to somehow propagate this last element on the left side into everybody on the right side. So yeah, so like I said, you have these 2 recursive calls. Assuming that you can solve these, the left half is finished. We need to push s sub n over 2 minus 1, which is just this last term, into every element onto the right. And this is the analysis. So we have n, the input is size n, we have n processors, and in the recursive call, we cut each in half. This is time log n, because that is the time to broadcast this last element into each one of these. And so that is log squared. Is this algorithm clear to people? This is the general plan. Yes. Yeah, sure. Good point. So broadcast is like you want to make this element, or you want to get this element into each processor on the right half, and there are n over 2 processors on the right half, and so like the most naive algorithm for broadcast is like this processor sends it to like one to its right, and then one, and then like the most naive algorithm would take time n because it would just like have to send it one at a time to all the different processors. It can take time log n because similar to like the tree-like reduction, like all the other processors can help in the broadcast. Like you push it into the middle, and then the middle one pushes it to its middle, and so on like that. Good question. Yeah. So that is so that is how you do broadcast in time log n, and you have to. This is recursive, so you have to do log n at every layer, and so the total time is log squared. So this is not bad. Log squared is actually okay, but ideally we would like to do better, something like log n, because log n is like what we had for sum, and we want to match the time. We want to do parallel prefix ideally in the time that it takes us to just do a sum from a theoretical standpoint. And how we're going to do that is this really cute trick, which is that we are going to do a little bit of extra stuff. So actually we can reduce this theoretical runtime from log squared to log by computing more, which is not obvious because usually computing more will take more time. But because it can happen in parallel, it doesn't show up in the theoretical bound. And the insight is that the thing that cost us log n was this term, which is the time to do the broadcast. And if we could somehow remove the broadcast, and the reason that we needed to do the broadcast is that everybody needed to have the total sum from the left side. But if we could somehow run the algorithm so that everybody on the right ends up with the total sum at the end, then you wouldn't need to do this broadcast term, and the total time would go to log. So this problem, the reason that we had to do the broadcast is that only one processor on the left side knew the total sum of the left side. But if every processor on the left side knew the total sum on the left side, then we could do one single round of communication. Everybody on the left half has a pair, like a neighbor in the right half, and then they all just send. And that's just one single round, and you don't need to do log n broadcast. And that is fine, because that is something that we can do in the hypercube, because everybody in the left half has some neighbor in the right half, you just flip the top bit. So what we're going to do is, rather than, well, in addition to computing the prefix, we're also going to compute the total sum on everybody in the left half. And we're going to send the total sum in the left half to the right half from every processor. So this is an example of how it's going to work. In the initialization, say we have 8 elements, and in the beginning, the elements are just like 1, 2, 3, 4, 5, 6, 7, 8. These are the different processors. And so in addition to keeping around the prefix sum, we're also going to compute the total sum on every processor. So there's 2 cases. One is that you're sending, so in every round of the communication, this is how it works. Like everybody has a neighbor, and the neighbors may get farther, but you can either know whether you're the right or the left. The left side is the right side. And so here, the left side is getting added into the right side because that's how the prefix works. Like it gets bigger left to right. So here, to compute the prefix, we are adding 1 plus 2. And also to compute the total sum, we're adding 1 plus 2. And basically, yeah, so the rule is if an element is coming in from the left, then you add the total sum, which is the red, into both the prefix and the total. Kind of similar to the upsweep a little bit. And if an element is coming from the right, then you only add the total sum to the total sum because there's no contribution to the prefix coming from the right. There's only contribution to the prefix coming from the left. There's contribution to the total sum coming from the right. So like you can see, this is the base case for the recursion. And just looking at these 2 processors, this black is the prefix and red is the total sum, because eventually we're going to wind the recursion all the way up, but this is like the most lowest level, and this is what's going to happen. We're going to compute the prefix and keep track of the total sum. And so we're going to do that in each pair. This is the prefix of these two processors, 3 and 7, and the total sum is 7 and 7. And so each of these gets paired in the beginning. This is 2. And now the prefix is localized into each of these pairs, and the total sum is also localized into the pairs. Yeah, and now we're just going to use that with farther neighbors. Oh yeah, and notice that all this communication is according to the hypercube, because this hypercube is like things that are distance 1 away from you are just flipping the lowest bit. But now if we want to go a little bit farther, this is flipping the second to the lowest bit in terms of the rank. And so we're going to compute the prefix and the total sum now of this entire block of 4. The way to do that is similar. We push some things left and some things right, and the rule is the same. If you push from the left, you update both the total sum and the prefix with the total sum, because the total sum is the sum of these two left things, and we already have computed the prefix here. So like I was saying, the issue is that the issue in the original formulation was that only the rightmost element knows the total sum. But now everybody knows the total sum, and so you can just push it directly into the right half. So 3 is the prefix in this node. 3 is the total sum in this node, and you add them up to get 6. 7 is the total sum in this pair. 3 is the total sum here, and you add them up to get 10. And then we follow the same rule. If things are coming from the right, then you update only the total sum. You don't update the prefix because there's no contribution to the prefix from the right. So now this 10 is the total sum of all the elements in this group of 4. Like 1, 2, 3, 4, you add them up, that's 10. And the prefix is now also correct, 1, 3, 6, 10. And we just do the same again on the right half. So the first step was to pair the neighbors right next to you. The second step is to pair the neighbors distance 2 away from you in groups of 4. And it's recursive, so like this group of 4 is finished. This group of 4 is not finished because they need to take in, if you added 10 to all of these, it would be done, because 10 is the total sum in this left half. And everybody in the right half has the prefix. And yeah, so the last step is you pair them all with something in the right half. You add in the total sum, and then the same right to left. This happens to be the end in this example, but like if we had more processors, we would just keep running the algorithm in higher levels. Questions? So it is a bit non-intuitive that this can reduce the runtime, because like we did do more summation, and we technically did do more sending. Like originally, like in the original one, you just had to do the broadcast at every level. But because the model that we're in says that all these lines happen in parallel, so their contribution to the total cost is only the cost of one line, because they're all sending and receiving from different pairs. And this is just the code. You don't have to exactly go through it, but this is what I was saying. Like there's two cases coming from the left and coming from the right. And you just find out your different pair, or you find out your neighbor by going up, this is the number of bits, and you find your neighbor by just flipping whichever bit it is, starting from the right. Yeah. So this is the start. You have two numbers, prefix and total, and you initialize them both as the input. Then you find your neighbor in this round. There are number of bits rounds. We send and receive the total sum. So we don't ever actually send or receive the prefix. We compute the prefix locally, but the only thing that gets sent is the total. Yeah, and we always update the total sum, but we only update the prefix if it's coming in from the left. Rank prime is your neighbor. So if your neighbor is to your left, then you update your prefix. Otherwise, you only update the total. What if n is greater than p? So now we have an algorithm. So we have, with this thing that I just showed, tnn is equal to log n, because it follows the same recursion that we had at the beginning. And under Brent's lemma, if you have p less than n processors, this is the time on p processors. So like parallel algorithms usually look like this when n is greater than p. Usually you do some kind of local computation, and then you need to send some result, at least one result from each processor to do some kind of reduction. So for prefix sum, like this is, so like when we were computing sum and n was greater than p, we did like a local sum on every processor, and then we did a reduction, and then we propagated that reduction. Or I guess with sum, you just need to do the one reduction and it's done. But with prefix sum, now you need to propagate it. So similarly in prefix sum, we compute it locally on each processor. So like here, you just sum up here, 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 here. And that takes time n over p, because we have n numbers, we have p processors, each one has a chunk of size n over p. And then, so that is this n over p time, and we compute, so, and then we have this additional log p, because we need to do a similar tree-like reduction on the last elements, first elements, I guess. So form the parallel prefix using the last local prefix. So after we do the local prefix, this in S sub 3, we have x0, x1, x2, x3. And now we need to push S sub 3 into all of these sums. So like just look at these left two. After doing the local prefix, we have the local prefix here, but we need to, like S sub 4 now has x sub 4, but we need also like the sum of x sub 0 up to x sub 3 in there. So we can do that by pushing in this last local prefix sum, and then once we have communicated that onto each processor, then we just do another kind of local reduction to push the last sum for the previous processors. Or you do kind of like a tree-like reduction to compute the prefix for every last one. So that is where this log p comes from. And the communication time is tau plus mu log p, because there are log p rounds of communication. And each one has startup cost tau, and you only need to send one element, mu. It's not totally right to do, so like it does work in the first, in this, just this pair, like to push in S sub 3. Like S sub 3 needs to go into all of these. But a little bit. So not totally right, for example, like it should be moving to the right rather than self. You don't need to add S sub 3 here, you need to add S sub 3 here. And you don't need to add S sub 7 here, you need to add S sub 7 here. And so to fix that, and the reason that we were doing this, of course, like when you actually see this example, we should not be adding S sub 3 into this thing, but with a regular prefix sum, like the start is equal to S sub 3. Like if we're just doing prefix sum on like S sub 3, S sub 7, S sub 11, S sub 15, to do regular prefix sum, the first element has S3. And we can just fix that by making it exclusive. So remember that exclusive means that you don't You want everything up to but not including yourself. So this is the same communication that we had before in this hypercube. But we don't need the total sum. Like this total sum is not going to get contributed into any of the prefixes. We need the exclusive sum, which is the sum up until each processor. So to do that, rather than initializing the prefix, so we still have these two parts, total sum, prefix sum, and total sum, but now we initialize prefix at 0. And then we'll get the exclusive version. Yeah, I only have a little bit left for this part. So to generate, yeah, so if you don't have a power of 2 number of processors, yeah, so there's a couple of leftover cases. One is that if n does not evenly divide p, that is fine. You can just, some processors will just get one more element than some other ones. But that's okay, because it just goes away in the asymptotics. The total local time is still order n over p. And if p is not a power of 2, basically what happens is that you find the next power of 2. So like you have actually p processors. P prime is some power of 2. P prime over 2 is also some power of 2. And you pretend that you have p prime processors, and you just ignore things that are from ranks greater than p. And that will work because the prefix sum algorithm is recursive. So like it will solve the subproblems correctly. Yeah, so this is an example. Like let's say you actually only have these processors. And you pretend that you have 8, but actually you only have 5. And you just don't, like if you are sending or receiving from something outside the range, then you just ignore that communication. I think that's all I want to say for today. Next time we will do applications. Thank you.